Has anybody here heard of a turducken? Or maybe a Bay Kraken? It's a cuisine of sorts. A turducken. So I apologize to my vegan-friendly folks in the session today, but a turducken is a composition of birds that some people like to eat. And basically, you take a chicken, you stuff it in a duck, and then that combination of birds gets stuffed into a turkey, and it's cooked. And from what I hear, it could be quite tasty. But the reason why I'm mentioning it is because it's an example of composition in the sense that you're kind of plugging birds into other birds, which now that I'm hearing myself say that, it's kind of grossing me out. But anyway, there's this newer type of composition called the Bay Kraken, where, and this is down, in the land down under, cue the Men at Work song, by the way. Basically, a chicken is stuffed inside of a crocodile, and the crocodile with the chicken in it is wrapped with bacon. And it's, of course, cooked on the Barbie. But that's another instance of, plugging meats into other meats, and I think I'm just going to leave it at that and go. I'm not sure how big of a crocodile. Big enough to fit a chicken in it, though. I'm quite hesitant to look it up online. I'm afraid of what I'll find. But by the way, do you guys know how to tell the difference between a crocodile and an alligator? Whether it sees you in a while or whether it sees you later. Yep, so whether it sees you in a while or sees you later. See you in a while, crocodile, or see you later, alligator. Truth. All right, well, we've encountered these sorts of operations with functions in the past. It's kind of an old-fashioned notation right here, which requests that you add the functions f of x and g of x together. Subtraction between two functions can also happen, and this would be the notation for it, f minus g of x, which is the same as just subtracting the two functions. If we want to multiply two functions, we could write it out this way, f times g of x, which is the same as f of x times g of x. And of course, if we wanted to divide two functions, we could write that as f over g of x, which is basically take the function f of x and write it on top of g of x. So these are the basic arithmetic operations that we can do with functions, addition, subtraction, multiplication, and division. There's something else that we can do with two functions, which is more akin to the turducken and Bay Kraken scenarios. Given two functions, f and g, we can form what's called a composition function, which notationally we'd see f circle g, or g circle f. That kind of looks like the word fog, which is why I have this meme here. And if we look at the left-hand side of what I wrote out up here in green, we have kind of like a starting notation, f plus g, f minus g, and so on and so forth. F circle g is kind of like a starting notation as well. We're seeing it right here where it's f circle g of x. And this can be rewritten as f, and in the parentheses of f goes the function notation for g. And what this notation is basically telling us to do is it wants us to take the function g of x and plug it into the function f of x. Okay, so this is notation for plug g of x into f of x. Now, I normally don't say it as f circle g of x. I'll usually say it as f of g of x, or if it's reversed, g of f of x. But we got to be careful you've probably learned that the word of means multiplication, and it does in certain contexts. In this context, when I say something like f of g of x, I'm referring to composition and not multiplication. So with something like f parentheses g of x, like we just wrote out up here, that doesn't mean multiply f and g together. It means plug g of x into the function f of x. So that's something that we have to be careful about. Or in short, the circle notation does not mean multiplication. You can go in the other direction as well. If we reverse and start out with g circle f instead of f circle g, this would be rewritten as g, and in its parentheses, f of x. And this would mean plug f of x into g of x. And I got a little cray with the memes in this section, but I found what is turning out to be one of my favorite memes regarding composition. And we're big Oreo fans here at the house. I feel like I'm buying them all the time when I go to Target. But I don't know about you guys. I feel like they're putting less and less cream in the Oreos. Like the double stuff Oreos seem like the regular Oreos from just a few years back. But anyway, you can think of composition with food. And I think I've just been talking about food this whole time. But anyway, imagine our function f of x are the 2 chocolate crackers for an Oreo, and g of x is the cream. Well, f of g of x would request that we plug g of x into the function f, and in this case, we would be taking the cream and plugging it into the crackers here to get the standard looking Oreos. Alternatively, if you switched the function notation for the composition and did g of f of x, and that would request that we plug the crackers into the cream to get what appears to be an inverted Oreo cookie sandwich there. Has anybody ever done that, by the way? Made a Oreo inverted? I haven't tried it yet. I'm wondering what it'd be like. I feel like the cleanup would be a little bit more, involved for g of f of x than f of g of x. But hopefully that illustrates the idea here. We're plugging functions into functions, and we're not doing those usual arithmetic operations with them. So to get to a legit example, I've got 2 functions here, f of x and g of x. And we're going to see just exactly what it means to form a composition. We're going to do it a couple of ways. The first is going to be f of g of x, and then we'll do g of f of x. So let's start with f of g of x. Recall that this is rewritten as f, and in the parentheses of f is g of x. Now, since we have specific expressions for these functions, I'd like to spell out just exactly what it is that we're plugging into the function f, and that would be the expression x minus 4. So anywhere we see an x in the function f, we're going to have to replace it with x minus 4. So visually speaking, this expression x minus 4 is going to get plugged into this x, and it's also going to get plugged into that x. Okay? So instead of x squared, it's going to be x minus 4 squared. Instead of plus 3x, it's going to be plus 3 times x minus 4. Then nothing to plug in with the plus 1. We'll just have to write it back down. Okay, so you guys see what I did there? All right. Now let's simplify. That square is going to require that we FOIL, and when we do, we're going to get x squared minus 8x plus 16. And we can distribute the 3 to clear parentheses for that. And of course our plus 1. And we'll combine all like terms. To get x squared minus 5x plus 5. Make sense? Let's do g of f of x. This is going to be rewritten as g parentheses f of x. And again, since we have a specific expression for f of x, let's spell out exactly what it is that we're plugging in. This time what we're going to be doing is taking x squared plus 3x plus 1 and plugging it into the x that's part of x minus 4. So again, we're plugging in x squared plus 3x plus 1. And let's go ahead and do that right now. So instead of x minus 4, it's going to be x squared plus 3x plus 1 minus 4. And that's going to simplify as x squared plus 3x minus 3. Any questions? Now, did we get the same expressions when we reverse the composition? No, we didn't. They're similar, but they're not exactly the same, right? So I want to make an important note here before we go to the next page. I'm going to say, in general, f of g of x does not equal g of f of x. There will be some cases where the reverse equals the original, but generally speaking, we can't expect it. We can't expect the two compositions to be equal to each other. Like for example, with the Oreos, we get a different type of sandwich, right? When we reverse f of g of x to get g of f of x. So there are, though, some instances where the two compositions equal each other, and we'll see more of those examples in the next section. But for now, I'd like to move on to how you evaluate a composition function. And keep in mind, evaluating is basically taking a specific number and plugging it into the variables. In this case, or in the context of functions, when we evaluate a function, we're plugging a number into it, right? So we know how to do that with ordinary functions, but how do we do it with a composition function? Well, basically, in a nutshell, there are two evaluations that you do to get the end result. And the order in which you perform the plugging in does matter. All right, so I have this diagram which illustrates how to evaluate the composition function f of g of x. So I'm going to refer to this notation in just a minute. But what happens is, once you have a selected value of x, that's your input, with the composition f of g of x, the first function that you plug it into is actually the function g of x. And then you get an output from that. So g of x will be a specific number once you've plugged a specific value of x into it. And that's not your final answer, but rather, it's kind of like a stepping stone to it, in the sense that whatever comes out of your first function gets plugged into your second function. In this case, it would be f of x. And then you get your final official output. So there's kind of two phases. You first plug your input into g of x. Whatever comes out of that gets plugged into f of x. And then whatever comes out of that is your official answer. Now with this notation, f circle g of x that I have here, I like to represent it this way. We first plug x into g of x, and then from there, whatever we get out of that, we plug into f of x. So it's kind of chain linked in this way. Let me show you how this works with two different functions for f and g, and now we have specific values of x. So in part A, we have f of g of 4. The first function that we're going to use is g of x. Okay, so we kind of work backwards. We go from right to left. So it is kind of a two-stepper here. Okay, we're first going to figure out what g of 4 is. Now keep in mind the expression for g of x is 2x minus 3. So we would replace x with 4 to get 8 minus 3, which gives us 5. That 5 is going to get plugged into the function f of x now. Okay, anybody want to tell me what we get when we plug 5 into f of x? Well, keep in mind f of x is x squared. Yep, so we would get 5 squared, giving us 25. Now, our second output here is our official answer. Okay, so the first output got morphed into an input of the function f of x. And whatever comes out of that second function that we use is our official answer. In other words, f of g of 4 is equal to 25. Okay, you want to give this a shot with part B? Give you a minute to work on that, then we'll go over the result. All right, you ready? So what's the first function that we're using this time? Yep. So we're going to plug -3 into the function f first. Okay, so let's work out f of -3. Okay, -3 quantity squared is +9. And that +9 is going to get plugged into our function g of x. Okay, so we're looking at 2 times 9 minus 3. 18 minus 3 should get 15. Okay, did we get 15? All right, so this means g of f of -3 is equal to 15. All right, for part C, we're going to use the function 2 times in a row. The first function we use is f. So let's work out f of 0. Okay, that's going to be 0 squared, giving us 0. And then we're going to plug that value back into the same function. So f of 0, again, which is 0 squared, which equals 0. All right, so f of 0 is 0. I'm going to add a part D to this, give you guys a shot. You can probably tell which one or which version of a composition I'm going to give you. I'm going to have you try g of -1. All right, so I'll check in about a minute, and we'll see how we did. All right, so we'll plug -1 into the function g of x. What did we get for g of -1? -5. Yep. And that's going to get plugged back into g of x. Okay, so we'll use 2x minus 3 again, this time with -5. We're looking at -10 minus 3, which is -13. All right, so g of -1 is equal to -13. All right, so you guys get the gist of how to evaluate compositions? Any questions before we move forward? All right, well, let's address the domain of a composition function. After all, there's a good chance that the two functions that we're using have different domains. So when we form a composition function, what the heck do we use, right? Well, I'm going to lead out with my bottom line here. Anytime we're trying to find the domain of a composition function, we have to form an intersection. And by intersection, I mean, what are the common elements or common numbers between both domains? And the two domains that we are going to try to intersect or figure out what's in common are the domain of what I like to call the inner function. Okay, so what I mean by inner function is the not the simplified, but the function that's getting plugged in. Let's say the plugged in function. As well as the domain of what I like to refer to as the new function. And in simple terms, this is the function after simplification occurs. Oops. Notationally, if I bring in f circle g of x, we can rewrite that as f parentheses g of x. And g of x in this instance would represent our inner function. Now, after everything has been simplified by plugging g of x into the function f of x, the simplified version of this expression is what I'm referring to as the new composition function. And in the next few examples that are on deck right now, I indicate the domains with D subscript notation. So if you look at this upcoming example, we have 3 bullet points here. And the first bullet point is labeled as D inner, or dinner. That represents the domain of the function that's getting plugged in. D new represents the domain of the simplified version of the composition. And then D F circle G, this is where our official answer for domain is going to be. And D F circle G refers to the intersection of both the D inner and the D new. So just giving you a little bit of foreshadowing here. Let's go ahead and start this example out. We have 2 functions, x squared minus 3 for f of x and square root of x for g. And they want a couple of things. They want the composition as well as its domain. So this is kind of a 2-parter here. For the first part, f circle g of x. Let's rewrite this as f of g of x. Now, we do have expressions for each of these. In particular, we know that g of x is equal to the square root of x. So basically, we're plugging the square root of x into the function f. So wherever we see an x in the function f, we're going to replace it with the square root. Case in point, instead of x squared minus 3, it's going to be square root of x squared minus 3. And this will simplify. Does anybody want to comment as to how this will simplify? Yep, so the square root and the power of 2 cancel out. And we're going to be left behind with x minus 3. So this is our composition function expression. And we're going to use it, in part, to help us find the domain. Let's start with d inner. Okay, the function that we plugged in was the square root of x. And we know that we're not allowed to plug any negative numbers into the square root function. So one way of expressing that is to say that the x values need to be greater than or equal to 0. And if you want a visual of that, you can draft up a number line, put 0 on it. We would bracket the 0 and shade to the right. Okay, so we used the square root to get d inner. Now for d new, we're going to use x minus 3. Now just visually speaking, with x minus 3, you'll see that there's no division by 0 possible. And because we got rid of the power of 2, with x minus 3, at face value, we wouldn't have to worry about square roots of negatives. All right, that would be the case if we weren't forming a composition. But as you're going to see with the intersection, we do have to worry about negatives still. But just taken at face value, x minus 3 would appear to have a domain of all real numbers. However, as it says above, the official domain is going to be the intersection of these two. So what's in common between both of these two number lines, dinner and dnew? Yep. So you could actually draw a little dashed line going through both number lines and going through 0. And the stuff that's to the right of this dashed line is what's in common. So anything from 0 to infinity, including the 0, is what's in common between both those two number lines. And this would give us our official domain of bracket 0, comma, infinity. Any questions about that?
I'm going to need you to explain that again. The
Okay.
dinner, dnew, and dfg, I don't understand that at all.
The dinner?
Yeah, how did you get the number lines from? I just don't know how you got the number lines.
Yep, so dinner refers to the square root of x. And in terms of domain, right, we're only allowed to plug in numbers that are greater than or equal to 0 into the square root of x. So that's how I came up with this.
Okay, because anything less than 0 is going to lead to that irrational number, right?
The imaginaries, yeah, exactly.
Right. Okay.
Yep. Now for dnew, I'm referencing x minus 3. So if we think about values of x that are allowed to be plugged into x minus 3, you can plug anything into x minus 3 because there's no division by 0 possible and there's no square roots in it anymore. So the domain of just the expression x minus 3 is going to be all real numbers. So if we had a function, I'll use a different notation. This is actually a linear function. And we know a linear function has a domain of all real numbers. So that's why I shaded this entire number line for dnew.
Okay.
I
got that now, and then I can obviously figure out the fog part. So, okay.
Yep. So for the official, domain of the composition, this part of each number line is shaded. So that's what's in common. And so we keep that part that's in common as our official domain.
Okay. Thank you.
No problem. Let's try this again. So 2 different functions, same instructions. Another 2-parter. We're going to want to find the composition function as well as the domain. So can I give you folks a moment to form f of g of x? All right, once you do that, if you see any opportunity to simplify, you may do so. We'll go over it and then we'll take care of the domain together. Okay, so here's what we're plugging into the function f of x. It's the expression 2x plus 1. So if this is going to go inside of the square root. So 2x plus 1, and then the minus 5. And that's going to simplify to 2x minus 4. And I think I'll leave it at that. So that's our composition function. We'll move to part 2. So d inner is going to refer to the expression 2x plus 1. Now, what do you guys think the domain might be for 2x plus 1? So 2x plus 1 is another one of those linear functions, format mx plus b. And all linear functions have a domain of all real numbers. Now, d new is going to refer to our composition function that we got from part 1. Do you think we need to worry about anything with the square root of 2x minus 4? Do you think it's possible to get some imaginary numbers with certain values of x with the square root of 2x minus 4? Definitely. So we have to make sure that 2x minus 4 at all costs is greater than or equal to 0. Otherwise, we get imaginary numbers. So what we can do with this fact is solve for x to get the specific x values that we can use with our composition function square root of 2x minus 4, at least that expression. So let's add the 4 over to get 2x is greater than or equal to 4, and then divide by 2. So it looks like with the expression square root of 2x minus 4, we would have to use x values that are greater than or equal to 2 for its domain. Now for the official composition function domain, I'm going to separate the two sections of the number lines by doing a dashed line through each of them going through 2. And which side of 2 do we have common numbers? Left-hand side of 2 or right-hand side? Right. So it looks like the part of the number line from 2 to infinity is what's in common. So the official domain for this function is going to be just that, bracket 2 comma infinity. So Kevin, how'd the second time around go for you?
Yeah, I got it. Thank you.
Yeah, no problem. Any questions about this example or domain, just in general? All right, let's do one more, and then we'll pull the plug on the notes, and we'll get to our review session. So I've mixed in rational functions with these domain examples. I want to show you how to form the composition, as well as, and I think what will probably be most important, is how to simplify the composition function, and then we'll get another round of trying to figure out the domain of it. So another two-parter here. We want the composition function and the domain. F of g of x. So what we're going to do is we're going to plug the expression 7 over x into the function f. So wherever we see x in the function f, we're going to replace it with 7 over x. And that would be right here. So we end up getting 3 over, instead of x plus 14, it's now 7 over x plus 14. Now with rational functions, we typically don't want fractions within the fraction. Case in point, by forming the composition, we have a fraction in the denominator of the bigger fraction. So what we end up doing is we focus on getting rid of this denominator x. And the way that we could get rid of the denominator x is to multiply the denominator of the entire fraction by x. But, you know, according to a golden rule of fractions, whatever you multiply to the bottom, you also have to multiply to the top. So we would have to multiply x to 3 on top as well. Everybody good with that? Now on top, x times 3 is just going to be 3x. On bottom, we distribute x to clear the brackets, in which case it'll cancel out the x that's underneath the 7, leaving behind 7. But when we distribute x to 14, we're going to have 14x now. Does that make sense? So this is our composition function, at least the expression for it. Let's move on to find the domain. So for d-inner, we want to examine what's not allowed to be plugged into 7 over x. There's one value of x that we should never plug into this fraction. What would that value of x be? 0. So I'm going to write x cannot equal 0. And on the number line, we're going to shade to the left of 0. When we get up to it, though, let's use parentheses. And then we'll shade to the right of 0. So anything but the number 0 can be plugged into our inner function. Now our new function has a value of x that we shouldn't plug into it, but it's not 0 this time. Anybody have an idea as to what value of x we shouldn't plug into our expression from part 1? Almost. -1/2 actually. So we don't want 7 plus 14x to equal 0. And if we solve for x here, that's going to tell us that x cannot equal -1/2. Okay, so on the number line, I'm going to go a little bit further to the left than 0 from that first number line, and we'll shade to the left and right of it. Now for the official domain, what I'm going to do is drop a dashed line through both the numbers 0 and -1/2. And let's figure out what's in common between both number lines. Is what's to the left of -1/2 in common between both number lines? Yep, so anything to the left of -1/2 is common. Is the stuff in between -1/2 and 0 in common? Let's see about that. This is from -1/2 to 0, and this is from -1/2 to 0. And both those parts are shaded. So those were in common, actually. What about the stuff that's to the right of 0? Is that in common? Yep. Maybe I'll change back to oops, yellow for the middle sections. I don't want it to be deceiving. So basically, everything is in common except for those two numbers, -1/2 and 0. Okay, -1/2 is shaded on the first number line, but it's not shaded on the second number line. 0's shaded on the second number line, but it's not shaded on the first number line. So the official domain is going to be anything from -infinity to -1/2, as well as the values between -1/2 and 0, and the values that are from 0 to infinity. So we're going to get 3 parts to our official domain in interval notation. And there it is. Is this all making sense? Anybody need me to re-explain any part of this problem? I didn't fry your brains, did I?